black holes as geometric cones. Black holes are often presented as exotic objects that require special rules, dramatic language, or force-driven narratives to explain their existence. This paper reframes them more conservatively. Black holes are not departures from gravitational geometry. They are its extreme but natural continuation. They arise when narrow gravitational cones exceed stabilization limits, producing terminal funnels in space-time geometry rather than objects formed by runaway force alone. In this view, black holes are geometry-first outcomes, not anomalies that sit outside the normal terrain of space-time. Within the terrain framework, cones represent sharply convergent curvature configurations. Unlike wells or cups, cones do not offer broad regions where trajectories can circulate, redistribute, or self-correct. Their defining feature is steepness. As curvature gradients intensify, allowable paths narrow rapidly, and stabilization mechanisms that operate in broader geometries fail. Matter entering such a region is not pulled in by an increasingly strong force in the classical sense. It is guided along an increasingly restricted set of geometric paths. Collapse in this framing is not an active squeezing, but the exhaustion of alternatives. Black holes form when this narrowing passes a critical threshold. Below that threshold, even steep geometries can still support bounded configurations. Energy redistributes, motion equilibrates, and structure persists. Above it, the cone becomes terminal. Trajectories converge faster than any known stabilizing process can counteract. At that point, space-time geometry no longer admits long-lived, outwardly connected paths. The result is not a violent snap, but a geometric inevitability, a region where future-directed paths overwhelmingly point inward. This explains why black holes are rare relative to stars. Most gravitational systems never sharpen into narrow cones. Stellar formation occurs in cup-like geometries where convergence is strong enough to ignite dense activity, but still broad enough to permit equilibrium. Radiation pressure, angular momentum, and redistribution processes operate effectively in these shapes. They are tolerant geometries. To produce a cone steep enough to become terminal requires conditions that defeat these stabilizers simultaneously. Such conditions are uncommon, not because black holes are forbidden, but because geometry usually saturates before narrowing that far. Seen this way, black holes are not exotic failures of physics, but predictable end states of a particular geometric path. If curvature continues to steepen without saturating, a cone forms. If the cone exceeds stabilization limits, it becomes terminal. Nothing about this requires invoking special substances, alternate universes, or speculative interiors. The event horizon marks where the geometry transitions from permissive to one-way. It is a geometric boundary of traversal, not a material shell. This framing also clarifies why black holes do not dominate the universe despite gravity being universal. Gravity explores a wide landscape of shapes. Wells and cups are far more common because they are dynamically forgiving. Cones require fine alignment of conditions and sustained steepening. When they appear decisively, but they do not proliferate casually. Black holes are therefore inevitable without being ubiquitous. Anchoring black holes in this way removes the sense that they are special exceptions, requiring special explanations. They are extreme geometries within the same terrain that produces galaxies and stars. The difference is not in kind, but in degree. Geometry that gently converges hosts structure. Geometry that sharply converges terminates it. Black holes sit at the narrow end of that spectrum. This paper exists to keep that continuity explicit. By treating black holes as geometric cones rather than force-driven oddities, the terrain framework remains unified. Nothing breaks when black holes appear. The map simply reaches one of its steepest features. Established physics already treats black holes as geometry-first phenomena rather than objects produced by an exotic new force. In general relativity, gravity is not modeled as a collapsing pull, but as space-time curvature that constrains allowable paths. Black hole solutions arise when curvature becomes so sharply convergent that future directed trajectories overwhelmingly point inward beyond the threshold. This is a geometric condition, not a material one, and it follows directly from the framework introduced by Albert Einstein. The defining feature of a black hole in theory is the existence of an event horizon, which is a boundary in spacetime beyond which outward-directed causal paths no longer intersect distant observers. This boundary is not a physical surface or shell. It is a limit of traversal defined by geometry. The mathematics does not require matter to be continuously forcing collapse at this stage. Once the geometry narrows sufficiently, the set of permitted geodesics changes qualitatively. Paths that once allowed redistribution and escape no longer do. This matches the cone interpretation precisely. As steepness increases, stabilization options vanish. Classical black hole solutions, such as those derived by Carl Schwarzschild, demonstrate this behavior explicitly. These solutions describe spacetime geometries where curvature gradients intensify smoothly until a horizon forms. Nothing in the solution requires exotic matter, alternate universes, or special interior physics to explain the horizon itself. The horizon is a geometric feature of the metric. Matter crossing it does not encounter a force spike. It simply follows the geometry available to it. This supports the view of black holes as terminal funnels in spacetime rather than as objects formed by runaway force. The rarity of black holes relative to stars is also consistent with geometric interpretation. Most gravitational systems reach equilibrium long before curvature sharpens into a terminal cone. Angular momentum, pressure, and energy redistribution naturally broaden convergence and favor cup-like geometries where stabilization occurs. General relativity does not predict inevitable collapse for all massive systems. It permits a wide range of stable configurations. Only under specific conditions does curvature continue steepening without saturating. This makes black holes inevitable outcomes of certain paths, but not common endpoints of gravitational evolution. Numerical simulations of stellar evolution and compact object formation implicitly rely on this geometric behavior. Collapse proceeds only when stabilizing mechanisms fail simultaneously and curvature gradients sharpen beyond recoverable limits. When those limits are crossed, the appearance of a horizon is abrupt and decisive, not gradual or negotiable. This aligns with the idea of a cone exceeding stabilization thresholds rather than a slow accumulation of force. Importantly, nothing in this interpretation addresses interior structure, information flow, or speculative extensions. The support rests entirely on exterior geometry and causal structure, which are well tested. Observational confirmations of horizons through gravitational waves and orbital dynamics around compact objects are measurements of spacetime geometry, not of interior composition. What is observed is how paths behave near steep curvature, not what fills the funnel beyond it. Taken together, horizon formation, classical solutions, equilibrium conditions, and observational signatures all support the same conclusion. Black holes are not anomalies bolted onto gravitational theory. They are extreme geometric configurations permitted by it. When spacetime curvature sharpens into a narrow, unsaturating cone, a terminal region appears. Black holes are the natural expression of that geometry, not a special exception to it.